Today we're going to focus on the operation of the JK flip-flop circuit. So let's begin by drawing a circuit. What we're going to do first is we're going to draw the SR latch circuit and then build the JK flip-flop circuit around that. Now you could design the SR latch circuit using two NOR gates or two NAND gates. For this particular video, I'm going to use two NAND gates. Now the input of the top NAND gate is going to become where it's going to be attached to the output of the other NAND gate, and the input of the bottom NAND gate is going to be connected to the output of the other NAND gate. So that's the SR latch circuit. Now to build the JK flip-flop circuit, we're going to add two 3-input NAND gates to this circuit. We'll call this input J and this input K. Now, there's 3 inputs to those two NAND gates on the left. One of those inputs will be connected to each other. We'll call this the clock input. The third input is going to be connected to the output of the other NAND gate. So we're going to attach this input all the way to the output of the bottom NAND gate. And this input here, we're going to connect that to the output of the top NAND gate. So that's how you can draw the circuit for the JK flip-flop. Now let's call the output of the first NAND gate S, and we'll call this R. And the final output we'll call Q, and the other one Q bar. Now let's review the truth table for NAND gate. If you recall, the truth table for an AND gate, well, first let me fill out the values of A and B. For an AND gate, the output is 1 only if both A and B are on. For the NAND gate, it's the reverse. The output is only 0 when both A and B are on the on state. So this is the truth table for a 2-input NAND gate. Now we can construct a truth table for a 3-input NAND gate, but here's what you need to know. The output is always going to be a 1 unless both inputs are 1. If both inputs are 1, the output will be 0. So for a 3-input NAND gate, all the inputs have to be 1 in order for the output to be 0. So in order for us to get a 0 for S, all 3 inputs must be a 1. If one of them is a 0, then the output is going to be a 0. Here's the formula for the output of a 3-input NAND gate. Let's use S and the 3 inputs A, B, and C. So S is going to be A times B times C, but it's the complement of that. So if we have 1, 0, 1, 1 times 0 times 1, that's going to be 0. The complement of 0 is 1. So the only way we're going to get a 0 here is if all three of these are 1. Using that formula will be 1 times 1 times 1, which is 1. The complement of 1 is 0. So keep that in mind as we discuss the operation of this circuit. We're only going to get an output of 0 if all the inputs are 1. Now, one of the first things we need to do before we discuss the operation of this circuit is decide what values Q and Q bar should be. We can make Q equal to 0, or we can make it equal to 1. So what I'm going to do, what I like to do, is set Q to 0 as our starting values. So what we're going to do is imagine if there's a push button for the J, K, and clock signal. We're going to push the clock button and we're going to press K. When we put an input of 1 to K, it's going to reset Q to 0. If we were to press the J button, it'll set Q to 1 if there's an active clock input. So that's what we're going to do right now. We're going to have an active clock input, and then we're going to press the K button. That's going to set Q to 0 and Q bar to 1. So that's going to be our starting values. Now what we're going to do is we're going to create a truth table for this circuit. So let's see if I can fit that here. We'll have our inputs J and K, and then the inputs for the latch circuit, S and R, and then the values of Q and Q bar, and then a description for the output. Now the first thing we need to consider is what happens when we don't have an active clock signal, or if the input at the clock is 0. If the input is 0, right now Q is 0 and Q bar is 1. But if the input is 0, it doesn't matter what the values of J and K will be. The output of the 3-input NAND gates, the values of S and R, will be 1. And let's talk about that. So we're going to have a 0 here and a 0 here. Now Q is 0, so this input at the K NAND gate will be 0. Q bar is 1, so the input for the top NAND gate will be 1 here. Now if J is 0, 0 times 0 times 1 is 0. The complement of 0 is 1. S is going to be 1. Or if J is 1, 1 times 1 times 0 is still 0. The complement of 0 is 1. So it doesn't matter what J is. S is going to be 1. The same is true for K. If K is 0, R is going to be 1. 0 times 0 times 0 is 0. Complement of 0 is 1. Or if K is 1, R is still going to be 1. Remember, the only time S or R will be 0 is if all three inputs are 1. If there's just a single 0 there, we're not going to get a 1 at S or R. If there's a single 0, it's the output is going to be 1. The only way we're going to turn this into a 0 is if all inputs are 1. So hopefully I didn't confuse you with that. So remember, the only way S is going to be a 0 is if we have a 1, a 1, and a 1. If there's a single 0, S and R will be 1. So if the clock is 0, doesn't matter what J and K will be. S and R is 1. Now, what happens when S and R is 1? In this case, when S and R has these values, the output is not going to change. Q is 0, so that follows the input here. This is 0. Q bar is 1, so that follows the input there. A 0 and a 1 will give an output of 1, which is the same as Q bar, so it's not going to change Q bar. And for a 2-input NAND gate, if the two inputs are 1, the output will be 0, which will not change Q because Q is already 0. Now let's see what would happen if Q had different values when S and R are both 1. Let's do it this way. So let's say Q is 1 and Q bar is 0. When S and R is 1, it's not going to change the values of Q. Whatever the values of Q are, it's going to remain the same when S and R is 1. So here Q is 1, so that means this input is going to be a 1. A 1 and a 1, 1 times 1 is 1. Complement of 1 is 0. So this becomes 0 here. 0 times 1 is 0. Complement of 0 is 1. So Q doesn't change, nor does Q bar change. So when S and R are both 1, whatever Q and Q bar, whatever values they have at that instant, they will remain at those values. So we can say that there's no change, or the circuit is in a state of memory. So what this means is that when we don't have an active clock signal, the output is not going to change. Whatever the values of Q and Q bar at that instant, it's going to remain at those values regardless if you press J or K. So the output can only change with an active clock signal or an active clock input. Now we're going to apply an active clock input, but we're not going to press the J or K buttons. What's going to happen in this case? Well, remember, S will be 1 if any of the 3 inputs are 0. So because J is 0, S is going to be 1. And because K is 0, R is going to be 1. So if J and K are 0, S and R will remain 1. And when S and R are both 1, the output is not going to change. The circuit will still remain in a state of memory. So there's going to be no change. Now what happens when we press J with an active clock input? What you need to know is that when you press the J button, you're going to set Q to 1. Now let's prove that. So right now we have a 1 at the clock input, J is 1, K is 0, Q is 0, so that means this input is going to be 0. Q bar is 1, so the top input will be 1. Now we have a 0 here, so R is going to stay 1. Now we have 3 1s at the top NAND gate. 3 1s will change S to 0. So now the output is going to change. So Q is 0. That means this input will be 0. A 0 and a 1 is going to give us an output of 1. So this is 1. A 0 and 1 will give us an output of 1. So Q has now changed from 0 to 1. Now that Q is 1, it's going to change this input. The 1 is going to follow here. So this is no longer a 0. 2 1s will make it 0. So that's going to change Q bar to 0. And of course, that will change this input. But 2 zeros will make a 1. And after that, there's going to be no more changes there. So Q is now 1. Q bar, we have to change that. That is now 0, as we can see here. S is now 0. R is 1. So when we press the J button, the result is that we set Q to 1. Now here's a question for you. At this point, what happens if we release the J button and then press the J button again with an active clock input? So first, let's release the J button. So J is going to go from 1 to 0. Right now, because Q changed, the inputs will change. So Q is 1. This 1 is going to go here, so it's no longer 0 at this input, but we now have a 1. Q bar is 0, so that's going to change this 1 to a 0. Now, when Q goes to 1, notice what happens. When Q goes to 1, that means that this NAND gate is waiting to be activated. It's now active, but it's waiting for K to be pressed. Q bar went to 0, so this input is 0. This NAND gate is inactive. Because now it doesn't matter if J is 0 or 1. S is going to be a 1 now. Remember, the only way we can get S and R to a 0 is if we have 3 1s at the input. So because Q bar is 0, and now this is 0, this NAND gate has been inactivated, which means S is locked into 1. So if you release J to 0, S is still going to be 1. If you press J to 1, S is still going to be 1. Right now, we haven't pressed K. K is waiting to be pressed. So because K is 0, R is 1. So notice what's happening here. Whether we press J to 1 or release J to 0, S is locked into 1. So both S and R are 1, and when that happens, there's no change in the output. So the first time we press J, we set Q to 1. If we release it, Q is going to remain at 1. If we press J again, Q stays at 1. So once you press it the first time, if you release, press, it's not going to change the output. The output is now locked into the state. So since we can't do anything with J after we press it the first time, since it's no longer going to change the output if we press it a second or third time, the only thing that's left to do right now is to press K. So with an active clock input, we're going to release J to 0, and we're going to press the K button. So J is now 0, K is 1. So right now, S is locked into 1 since Q bar is 0. Now, once we press K, when Q is 1, we have 3 1s at the input. That's going to change R to 0. So S is 1, R is 0. Now that the values of S and R have changed, the output will change. So at this instant, Q is initially 1. So we have a 1 and a 0. That will give us an output of 1. So that's going to change Q bar to 1. Okay, let's just get rid of the values here so I don't have to write this twice. So now that Q bar is 1, the input at the top NAND gate will be 1. And 2 1s, 1 times 1 is 1, complement of that is 0. That's going to change Q to 0. And when Q goes to 0, this input will be 0. And 2 zeros will give an output of 1, which Q bar is already 1. So when we press the K button, we reset Q back to 0. So Q is 0, Q bar is 1. Now what happens after we press the K button once? What happens if we release the K button and then press it again? Now that Q and Q bar have changed, the K NAND gate is inactive. The J NAND gate will be active. So if we release K and then press K again, it's not going to change the output. Because Q is now resetted back to 0, this input will be 0. And that's going to deactivate the bottom NAND gate. Q bar is 1, so now the top NAND gate, or the J NAND gate, is now active and waiting to be pressed. So now that Q is 0 and the K NAND gate has been deactivated, if we release K to 0, R is still going to be 1. Remember, R will only be 0 if we have 3 1s here. So because Q is 0, we can't have 3 1s anymore. So R is going to be 1 regardless if we release K to 0 or if we press K to 1. So remember this, when Q is 0, the K NAND gate is deactivated, which means if you press or release K, even if there's an active clock input, the output is not going to change when Q is 0. Pressing and releasing K will not affect the output. And when Q is 0, because the K NAND gate is deactivated, that means that the J NAND gate will be activated because Q bar is 1. So the J NAND gate is waiting to be pressed, and that's going to change the output of the circuit. When Q bar is 0, the J NAND gate will be deactivated, which means if you try to press J or release J, it will not change the output. And when Q bar is 0, the K NAND gate is activated, so it's waiting for K to be pressed. Once you press K, it'll change the output. So make sure you understand that. When you press K, after you press it the first time, the K NAND gate is deactivated, the J NAND gate is activated, waiting to be pressed. The output will only change once you press J. After you press J the first time, if you press it again, the output won't change. Once you press J, the J NAND gate will be deactivated, but it's going to reactivate the K NAND gate, waiting for K to be pressed, and it's constantly going to flip-flop. So when you press J once, the output changes. You press it again, it doesn't change. The output's only going to change when you press K. If you press K a second time, the output's not going to change. It's only going to change when you press J, and it's constantly going to go back and forth like that. Now, I know I did a lot of talking, but I want to make sure I can simplify this so that you understand it well. When you press J the first time, you set Q to 1. If you press it a second time, the output is not going to change. J is deactivated. The only thing you can do at this point is press K with an active clock input. Once you press K, you reset Q back to 0. And after you press K the first time, the K NAND gate is now deactivated. If you press K a second time, the output's not going to change. All you could do now is press J. When you press J, Q goes back to 1. If you press J a second time or release it, then press it again, Q is not going to change. J is now deactivated, K is activated, waiting to be pressed. You press K, Q goes back to 0. Press K again, Q stays at 0. until you press J, which makes Q go back to 1. So that's how this JK flip-flop works. It only switches state when you press J or K once. Pressing it a second time will not change the state. You have to press the other button with an active clock input. So now that we've considered all that, what's going to happen if we press J and K at the same time with an active clock input? So right now, we've pressed K. We're going to hold on to K with the current circuit conditions, and then we are going to press J. So what's going to happen? At this instant in time, Q is 0 and Q bar is 1. So we have a 1 at J and a 1 at K, which is already there. Feel free to pause the video and think about what's going to happen here. So because K is deactivated, because Q is 0, R is going to be 1. Q bar is 1, so the J NAND gate is activated. Because we have 3 1s at the input, S is going to be 0. Now for you to understand what's happening, I'm going to make another table with Q and Q bar. Right now Q is 0 and Q bar is 1. When S becomes 0, we have a 0 and a 1. That's going to make the output 1. So Q is going to change to 1. So Q is no longer 0. Now this is going to change here. So this is going to become a 1. And that is going to make Q bar 0. Now that Q and Q bar have changed values, the J NAND gate is going to be deactivated and the K NAND gate is going to be activated. So the inputs at J and K, or those two NAND gates, will change. So Q is 1. So this 0 is going to become a 1 now. And Q bar is 0, so this input here is now 0. So that's going to affect the values of R and S. The K NAND gate is activated. We got 3 1s. That's going to change R to 0. And S is going to change to 1 because it's now deactivated with this 0 here. Now because S and R changes, that's going to change the value of Q and Q bar. So at this instant, when Q is 1 and R is 0, that's going to make Q bar 1. And now here Q bar is 1, S is 1, that's going to make Q 0. Now let's do this one more time. So now that Q is 0, it's going to deactivate the K NAND gate. So this changes to 0. Q bar is now 1, so that's going to reactivate the J NAND gate. This turns to 1. These 3 1s will make S is 0. And because we have a 0 here, R is going to be 1. And this is going to once again change Q and Q bar. So Q is initially 0. So we'll change this to 0. 0 and 1 will make a 1. So Q bar is 1, S is 0. That's going to change Q to 1. And now when Q is 1, this input changes. 1 and 1 will make Q bar 0. And this cycle is going to keep repeating itself. So Q is going to change from 0 to 1, 0 to 1, and it's going to keep doing that. Q bar is going to remain the complement of Q, so it's going to go from 1 to 0, 1 to 0. So I'm just going to call this Q, and I'm going to call this Q bar. So they're constantly going to alternate. But to be more specific, when S is 0 and R is 1, we see that Q is 1 and Q bar is 0. Which matches what we see here. And in the previous condition, we saw that when S is 1 and R is 0, Q is going to be 0 and Q bar is going to be 1. Now, how do we describe this? What's happening here? For the output, the description here is toggle. Toggle means a switch in action. So right now that we say that the circuit is toggling, like Q is toggling back and forth between 0 and 1. And Q bar is always going to be the complement of Q. And these two are just toggling, switching states, going back and forth. So I'm going to put a line here. So with an active clock input, and when J and K are 1, S is going to toggle between 1 and 0, R is going to toggle between 0 and 1, Q is going to toggle between 0 and 1, and Q bar is going to toggle between 1 and 0. So the values of S, R, Q, and Q bar, they're constantly switching states. When S and R, when it's 1, 0, Q bar will be, Q will be 0, Q bar will be 1. And when S and R, when it's 0, 1 respectively, Q and Q bar will be 1, 0 respectively.